Hello and welcome back to another geometry read-along. Today's section is 3.2 from College Geometry, a problem-solving approach. This is more area formulas. The rectangles and triangles are not going to be enough for us. For example, take a look at this guy. A single 4-inch diameter water pipe is to be replaced by smaller 2-inch pipes. How many 2-inch pipes will be required to carry at least as much water as the 4-inch pipe? Right, so we need, in effect, the area of this cross-section. We need to be able to replicate that with a number of 2-inch pipes so you get the same throughput of water. How many is it going to take? How do I find the area of this circle? Let's find out. First up, area of a parallelogram. Now that we can use theorem 3.3 to find the area of any triangle, we can use postulate 3.2 to find the areas of other common polygons. The theorem is found in the previous video. We'll get to the postulate here soon. So for example, how about finding the area of the parallelogram in figure 315a? So that would be this guy here. How would you do that? It's not a rectangle and it's not a triangle. But if we draw a diagonal BD, shown here in figure B, we form two triangles having the same size and shape. We can prove that later in chapter 5. Thus, the area of quadrilateral ABCD is twice the area of triangle ABD. Okay? Because the height of triangle ABD is 6 inches, and we have that altitude drawn in, but now it's the altitude of a triangle, and the base has measured 8 inches. Its area is 1/2 times 6 times 8, or 24 inches squared. Because triangle ABD and triangle CBD are identical triangles, each with an area 24 inches squared, by postulate 3.2, the area of the parallelogram is 2 times 24, 48 inches squared. That postulate was the one that said we can add areas together to form the total area of a composite shape. Notice that we could have found the area in example 3.8 by multiplying 6 inches, the height of one of the triangles, by 8 inches, the length of the base of one of the triangles. Well, yeah, why didn't we just do that? That would have been faster. Yeah, but we didn't know that we could do that yet, not for sure. In a parallelogram, the length of a perpendicular segment having one end point at a vertex and the other end point on the opposite parallel side. The length of a perpendicular segment. Okay, so that's drawing it. They're describing this 6-inch line here, right? Perpendicular segment, so perpendicular from a side. One end point is at a vertex, right there, and the other end point is on the opposite parallel side, or the side extended, is called the height of the parallelogram. Okay, so very technical, drawn-out definition for the height of the parallelogram, the distance between two parallel sides. As is the case with triangles, a height is associated with a particular side called the corresponding base of the parallelogram. We have the corresponding base is drawn with that height, or is connected to that height. Example 3.8 leads to the following general result. We will leave the verification for the problem set. Theorem 3.4, area of a parallelogram. The area of a parallelogram is equal to the product of the length of one of its sides and the height to that side. Emphasis on the to that side. Make sure those two things, as I mentioned in class, whenever you are finding the area of something, you need to be multiplying two perpendicular quantities, two perpendicular lengths, so the base and its perpendicular height. In chapter 5, we will prove that a rhombus is a special type of parallelogram. Thus, the area of a rhombus can be found using the formula in theorem 3.4. So here it is in action. You wanted the shortcut, here's shortcuts. Find the area of the rhombus ABCD in figure 316. Here it is. Notice we have a side length there, and this guy is the only right angle seen outside of the rhombus. That seems like a weird way to draw it, but it works. It is from the vertex of one side and goes to perpendicular against the other side. That's a height. Any side of the rhombus may be used as the base. We will use segment BC since the height to that side is given. A rhombus has 4 congruent sides, so BC equals CD equals 6 centimeters. Thus, the area of ABCD is given by A equals B times H, 6 times 4.5, or 27 centimeters squared. Area of a trapezoid. The same technique used to derive the formula for the area of a parallelogram can be used to find a formula for the area of a trapezoid. So here's an example. Find the area of the trapezoid in figure 317A. So from this trapezoid given, how are we going to find the area of this? We've got 2 parallel sides. We've got looks like a height. Okay, it's perpendicular there. Solution. If we draw a diagonal BD, see figure B, so now we're drawing in this diagonal, we form triangle ABD and triangle BCD. These are not congruent triangles like last time. Thus, the area of ABCD is the sum of the areas of the 2 triangles. But at least that still works. We can still add them together. Because the height of both triangles is 5 centimeters, and the bases are 10 centimeters and 6 centimeters, the area of the trapezoid is, wait, let's verify that. So we've got base 10, height 5. Here we have other triangle of base 6, and if you extend this out so you can go perpendicular to the other vertex, you will have the same height of 5. So the area is 1/2 10 times 5 plus 1/2 6 times 5, which equals 25 plus 15, or 40 centimeters squared. Notice that 1/2 10 times 5 plus 1/2 5 times 6 can be written as 1/2 5 times 10 plus 6. That's just factoring out the common values there. This leads to the following general result, whose verification we will leave for the problem set. The height of a trapezoid is the perpendicular distance between the 2 bases. Ooh, that's a much simpler definition. Let's include that one in our notes. And of course, the full theorem here. Area of a trapezoid. The area of a trapezoid is equal to half the product of the height and the sum of the lengths of its 2 bases. And there's the algebraic formula down there. Hey, rectangle, could you be a little bit... There we go, that's better. Okay, moving on. So let's see, using that fresh new formula in action, example 311, find the area of the trapezoid in figure 318A in 2 different ways. 2 different ways. Well, okay, first way we have solution using theorem 3-4, right? Here's the trapezoid area formula. So 1/2 height times base 1 plus base 2 equals 1/2 times 10, that's the height, times 15 plus 20 equals 175 inches squared. Another way to do it, since this is a right trapezoid, we can subdivide the trapezoid into a rectangle and a right triangle, as in figure 318B. Over here, we've added in an extra line. You can always add in extra lines, divide things into smaller pieces. So here we have the area is going to be a length times width of the rectangle plus 1/2 base times height of the triangle. So that will be 15 times 10 plus 1/2 5 times 10 equals 150 plus 25, or 175 inches squared. How about a regular polygon? Not just hexagon, as we can clearly see here, but for any regular polygon. We can show that there is a point in the plane that is equidistant from all vertices of a regular polygon and from all the sides of a polygon. This point is called the center of the polygon. Ooh, that's good. That's good, because we've had centers of circles before, but we haven't officially had the center of a polygon, but it absolutely makes perfect sense to exist. So figure 319A, that point O is the center of the regular hexagon. we can conveniently find the area of any regular polygon by subdividing the polygon into triangles as suggested by the regular hexagon in 319a. Right? They have then added in lines from that center point to each vertex, and you create all these identical small triangles. The area of each of the 6 triangles is 1/2 s times h, where h is the perpendicular distance from the center of the polygon to any side, C and B. So now we've taken that triangle and drawn in its height here from the side up to the center. The line segment with length h is called an apothem of the polygon. So that is, this is our definition of an apothem, right? Thus, the area of the hexagon is 6 times 1/2 s times h, because there were 6 total triangles, right? We can rewrite this equation as 1/2 h times 6s, which is equivalent to 1/2 h times p, where p equals 6s. That's the perimeter of the hexagon. We can generalize this technique to any regular polygon. This is the content of the next theorem. Okay. Now, the reason you would change this equation into one that is based on perimeter is so that I can generalize this and apply this exact formula for any regular polygon. Notice this now does not depend on the number of sides in my polygon. It's whatever the perimeter is. Okay? The perimeter calculating will depend on side length and number of sides. But for my area formula, I don't need to restate that. So area of a regular polygon is equal to half the product of the perimeter of the polygon and the perpendicular distance from its center to one of its sides. Make sure to add that to your notes. And let's see it in action. Example 312. A bandstand in a city park is to be constructed in the shape of a regular octagon. Oh, they're getting fancy. To estimate the lumber needed, we must calculate the area of the platform. Using the dimensions given in the figure, where point O is the center, determine the area of the octagon. So here we have, looks like a side length of 10 and an apothem of 12.1 feet. So using theorem 3.6, we have area is 1/2 perimeter times h, or 1/2 times 8 times 10, so 8 sides times 10 feet each, times apothem 12.1 equals 484 feet squared. There we have it. Now, what about that circle that we needed for the problem from the beginning? How do we get the area of a circle? Imagine a series of regular polygons as shown in figure 321, where h remains constant, but the number of sides increases to approach a circle. So we started with the triangle here, 3 sides, 6 sides. Looks like 4, 8, 12 sides, dodecagon, all the way out to infinite sides, such that every side length comes down to a single point. That is a true circle, but it's still the same. You still have that height from the center to the edge times the perimeter, except we start changing the names around. The height in theorem 3.6 becomes the radius, r, of the circle, and the perimeter, p, becomes the circumference, c, of the circle. Thus, by substituting r for h and c for p in the area formula in theorem 3.6, we find that the area of a circle of radius r is equal to 1/2 r times c. That is a perfectly valid, perfectly reasonable area formula for a circle, but we know what c is. C is equal to 2 pi r, so we can substitute that back into this formula and simplify to get pi times radius squared. The area of a circle then is equal to the product of pi and the square of the radius. And as a reminder, remember pi is that wonderful transcendental number, approximately equal to 3.14159, and so on. Let's see it in action. Right, this isn't just a circle. Ooh, they're getting more complicated on us. Figure 322 is composed of one large and four small semicircles. Find the area enclosed by these 5 semicircles. So we've got the big one out here, and then we've kind of cut into it with these 4 smaller scallops there. Almost reminds me of the shape of something a particular like vigilante might want to throw as a weapon. So the diameter, capital D, of the larger semicircle is 16 inches, as shown there in the diagram. So its radius, capital R, is 8 inches. The diameter, lowercase d, of each small semicircle is 16 divided by 4, or 4 inches. So the radius, little r, is 2 inches. The area of the large semicircle is area of, and you got to put some subscript here to distinguish which areas we're talking about. So let's call this area large. Area L is 1/2 pi big R squared. Substitute 8 for big R, and you get 32 pi inches squared. And then the area cut out by the 4 small semicircles is area small, would be 4 of them times 1/2 pi small r squared. Substitute 2 for small r. Notice that 4 times the 1/2 reduces to a 2. Simplify that. And we get 8 pi inches squared. Leave it in terms of pi for now. Thus, the total area is given by a total is the large area minus the small area. If it helps, if you need to know, when do I need to know? Do I take the area away or do I add to it? I want you to imagine this shape made out of cookie dough. Okay? You are baking some delicious cookies, and you've only got one semicircle, or actually, well, you've got a large and a small semicircle cookie cutters. How do you do that? How do you create this shape out of cookie dough? You would first cut out a semicircle, and then you would cut out from that, you would take away these small ones. So large minus small is 32 pi inches squared minus 8 pi inches squared. We've got matching units. And we've got, in terms of pi, you can kind of treat pi as a variable here. So it's 32 of them minus 8 of them leaves 24 pi inches squared. The exact area, almost time for lunch, of the shaded region is 24 pi inches squared. For many practical applications, a decimal approximation is more appropriate. So in this case, let's find that 24 times pi will give us about 75.4 inches squared. Following table summarizes the area formulas we have discussed so far. Oh my gosh, one handy-dandy chart with all the area formulas. This is the kind of thing you will often see in the back of planner books and so forth, where they give you all the area formulas for easy reference. So go ahead and make sure you've got that in your notes. Maybe put it on a note card and have it handy while you're doing your problem set. Right, but there you go. Rectangles, right triangles, non-right triangles, parallelograms, trapezoids, regular polygons, and circles. So, how about that pipe? To replace a 4-inch pipe with 2-inch pipes, the total cross-sectional area of the 2-inch pipes must be at least as great as the cross-sectional area of the 4-inch pipe. A 4-inch pipe has cross-sectional area of pi times radius squared. With a 2-inch radius, we get 4 pi inches squared. A 2-inch pipe has cross-sectional area of, well, 2-inch diameter pipe has a 1-inch radius, so just pi inches squared. So that means you will need 4, right? Because this 4 pi is 4 times as big as 1 pi. So you'll need 4 2-inch pipes to have the same cross-sectional area as one 4-inch pipe. There you go, pretty handy. And one final note here on geometry all around us. Take a look at this diagram here of the cars produced per year in the United States versus Germany. And they've included a lovely little pictorial representation of the relative value of those numbers. So the pictograph to the left compares the number of cars that two different countries produce in a year. The graph is deceptive, however. Oh no. Using the numbers given, we see that the production of cars in the United States is roughly twice that of Germany, right? 11 million versus, well, almost 12 million versus 5.6, closing in on 6 million. Yeah, about double. However, the car symbol for the United States appears to be about 4 times as large. The reason is that both the length and the height of the car were doubled, which results in the area being quadrupled. Just imagine trying to copy and paste this car on top of that one. You could fit 4 of these, one here, 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 and here, right? Into like kind of 4 corners to fill that space. Okay? Your brain is naturally going to measure things in terms of area. How much space is this taking up entirely, since it is a full 2-dimensional image? To represent an accurate 2-dimensional comparison using the car symbols, where one represents n times as many cars as the other, either of the following is correct. A, one of the dimensions of the first car should be displayed as n times the corresponding dimension of the second car, and the other dimension of the 2 cars should be exactly the same. That would be, we take the Germany car, and for the United States, we will make it twice as long, but we will leave it the same height. Okay? Copy it up here, same height, but make it twice as long. It's going to look a little funny, though. Or both dimensions of the first car should be square root of n times those of the second car. Because the area gets squared, we take all the dimensions, square root them. So in this case, if we wanted to double it, we would have the square root of 2 times the height and square root of 2 times the length to get your new car dimensions. All right. Hope you found this helpful. Thank you very much for listening. Enjoy the rest of your day.